There was a time when gravity seemed to be the unquestioned ruler of the cosmos. Apples fall. Planets orbit. Stars gather into galaxies. Galaxies merge into clusters. Across every scale we could observe, gravity appeared to pull matter together, like an invisible thread stitching the universe into a single cosmic fabric. This expectation feels so natural that we rarely notice how deeply it shapes our intuition. When you throw a stone into the air, it slows down before falling back to the ground. When you pour water, it always flows downward. Nearly everything in our everyday experience suggests that motion tends to bring things together, not pull them apart. That is why, when astronomers first began studying the expansion of the universe, they assumed gravity would act as a cosmic brake. The Big Bang may have sent galaxies rushing away from one another, but over immense stretches of time, gravity should gradually slow that expansion. Given enough time, perhaps everything would eventually reverse course and collapse back together. It seemed like a perfectly reasonable story. Until the universe answered with something no one expected. Near the end of the 20th century, astronomers carefully measured the brightness of extremely distant exploding stars known as Type Ia supernovae. These stellar explosions serve as cosmic landmarks, allowing scientists to calculate enormous distances across space with remarkable precision. And that is when the discovery that transformed modern cosmology emerged. The universe was not slowing down. It was speeding up. Imagine throwing a stone into the sky only to watch it accelerate farther away from Earth instead of falling back down. Everything your intuition has ever taught you says that should be impossible. Yet on cosmic scales, that is precisely what appears to be happening. But this is still only the surface of the mystery. Because this discovery forced physicists to give a temporary name to something they did not understand. Dark energy. The name sounds as though it explains something. In reality, it simply acknowledges our ignorance. It tells us that there exists something invisible, immensely powerful, and unlike any ordinary form of matter ever observed. And here is the detail that changes everything. The most intriguing explanation suggests that empty space itself possesses energy. Pause for a moment and think about how strange that idea truly is. When we imagine a perfect vacuum, we imagine nothing at all. No air. No dust. No atoms. No light. Simply emptiness. Modern physics tells a very different story. According to quantum mechanics, empty space is never truly empty. Invisible quantum fields constantly fluctuate. Particles appear and disappear over unimaginably tiny intervals of time. Space behaves less like absolute nothingness and more like an ocean whose surface never becomes completely still. Intuition tells us that nothing should happen inside nothing. Physics tells a different story. And the mystery becomes even stranger when we move to the next layer. If empty space contains energy, then as the universe expands, more space comes into existence. And if every newly created region of space carries the same tiny amount of vacuum energy, then the total amount of dark energy grows together with the expanding universe itself. At first glance, that seems impossible. After all, we learn that energy cannot simply appear out of nowhere. So how can the universe continue gaining dark energy as it expands? This is where intuition begins to fail. General relativity describes an expanding universe in a far more subtle way than everyday physics describes a closed laboratory. The mistake lies in assuming that the entire cosmos must obey exactly the same simple rules we use to understand ordinary objects. The truth is that the universe does not behave like the objects we use to understand it. And once we accept that, an uncomfortable consequence emerges. The laws that appear permanent in our daily lives may be nothing more than local approximations of something far deeper. Now consider this. Imagine hundreds of dots drawn across the surface of a balloon. As the balloon inflates, every dot moves farther away from every other one. None of them is the center. None is actually traveling across the surface. The surface itself is expanding. The universe appears to work in much the same way. Galaxies are not simply moving through empty space like debris from an explosion. Space itself is stretching between them. And dark energy appears to be driving that expansion faster and faster. What this means is far more unsettling than it first appears. There are regions of the universe whose light may never reach us again, not because light has stopped traveling, but because the space between us and those distant regions expands faster than light can ever cross it. Imagine standing on a moving walkway that continuously accelerates while someone walks toward you from the opposite end. Eventually, that person keeps walking, yet never reaches you. That is unsettling because it breaks one of our deepest assumptions, the belief that enough time can overcome any distance. But the cosmos may contain distances that not even time itself can conquer. And this is only the first layer of the mystery. Now consider this. Imagine waking up tomorrow to discover that every city on Earth is slowly drifting away from every other city. The roads stretch. The oceans widen. Continents separate a little more every second. At first, the change would be imperceptible. Then distances would become impossible to cross. Eventually, every civilization would disappear beyond the horizon, isolated forever. On a cosmic scale, something remarkably similar is already happening. The expansion of the universe does not merely increase distances. It gradually erases the possibility of future contact. Every second that passes carries distant galaxies farther beyond our reach, creating invisible boundaries that no spacecraft, no signal, and perhaps not even light itself will ever overcome. This is where the story becomes deeply unsettling. We often imagine the universe as an eternal stage where stars are born, galaxies collide, and cosmic history unfolds endlessly. But if dark energy continues behaving as it appears to today, the future of the cosmos may become increasingly empty, not because matter disappears, but because everything becomes permanently isolated. This is still only the surface. The problem grows even stranger when we remember that gravity has shaped the universe for nearly its entire history. Shortly after the Big Bang, matter was densely packed together. Gravity slowly amplified tiny irregularities in that primordial matter, allowing clouds of gas to collapse into stars, stars to gather into galaxies, and galaxies to assemble into enormous clusters. Everything we see in the night sky exists because gravity patiently built structure over billions of years. Dark energy appears to be doing the opposite. It does not tear galaxies apart directly. Instead, it weakens gravity's influence across the largest cosmic scales by continuously stretching the fabric of space itself. Imagine trying to pull two magnets together while someone steadily stretches the table beneath them. The magnets still attract one another, but the surface separating them keeps growing. That is a simple image of what may be happening throughout the universe. The intuition says gravity should eventually win. Physics suggests something very different. Current observations indicate that dark energy now dominates the overall evolution of the cosmos. In fact, ordinary matter, the stars, planets, gas clouds, and even ourselves, accounts for only a small fraction of the universe's total energy content. Dark matter contributes much more than visible matter, and dark energy appears to be the largest component of all. Think about that for a moment. Everything humanity has ever touched, every mountain, every ocean, every civilization, every animal, every person who has ever lived, belongs to a tiny visible fraction of reality. Most of the universe is made of things we still do not fully understand. That realization alone changes the way we think about existence. But here is another detail that changes everything. The equations describing dark energy work astonishingly well. They match observations of distant supernovae, the large-scale distribution of galaxies, and the cosmic microwave background with remarkable precision. And yet, when physicists attempt to calculate the vacuum energy predicted by quantum mechanics, they obtain a result so enormous that it exceeds the observed value by roughly 120 orders of magnitude. This has been called the worst theoretical prediction in the history of physics. Imagine estimating the height of a building and accidentally predicting something larger than the observable universe itself. The discrepancy is not small. It is almost unimaginably vast. Somewhere, one of our fundamental assumptions must be incomplete. But which one? This question has haunted theoretical physics for decades. Perhaps quantum field theory is missing an essential ingredient. Perhaps gravity behaves differently under extreme conditions. Perhaps dark energy is not vacuum energy at all. Or perhaps the answer lies within a deeper theory that humanity has not yet discovered. Each possibility opens an entirely new layer of mystery. And every new layer reminds us of something profoundly humbling. The more accurately we observe the universe, the more clearly we recognize how much remains unknown. There was a time when we believed the stars were fixed lights attached to a celestial sphere. Later we learned they were distant suns. Then we discovered galaxies beyond our own. Now we find ourselves confronting a universe whose largest ingredient has no confirmed physical explanation. That is not a weakness of science. It is one of its greatest strengths. Science advances not because it possesses all the answers, but because it is willing to admit when reality is more mysterious than expected. And perhaps no mystery illustrates that better than dark energy. Because the deeper we investigate it, the less certain we become that we truly understand what the universe itself is. But here is the problem. Everything we have discussed so far assumes that dark energy remains exactly as it is today. It assumes that its strength never changes, that it continues to accelerate the expansion of space at the same gentle but relentless pace. The truth is that we do not know whether this assumption is correct. And that uncertainty opens the door to one of the most unsettling possibilities in modern cosmology. Imagine standing on a frozen lake. At first glance, everything appears perfectly stable. The surface is smooth, silent, and solid beneath your feet. But deep below the ice, invisible cracks slowly spread outward. Nothing seems wrong, until the moment the entire structure suddenly gives way. The universe itself may be resting on a similar uncertainty. If dark energy is truly constant, then the future of the cosmos is likely to end in what scientists call the Big Freeze. Galaxies will drift farther apart. New stars will eventually stop forming. Existing stars will exhaust their nuclear fuel and fade into darkness. Black holes will slowly evaporate over unimaginable spans of time. Eventually, the universe could become an immense, cold expanse where almost nothing changes anymore. It is a future defined not by violence, but by silence. Yet this is only one possibility. The next layer is far stranger. Some theoretical models suggest that dark energy may not remain constant forever. Instead, it could gradually grow stronger as the universe expands. At first, this difference appears insignificant. But over billions of years, even the smallest change can reshape the destiny of everything. If dark energy continues increasing without limit, gravity may eventually lose every battle it still manages to win. Galaxies would separate permanently. Then galaxy clusters would dissolve. Later, individual galaxies themselves could begin to lose their structure. Eventually, even solar systems might no longer remain gravitationally bound. And the process would not necessarily stop there. This hypothetical scenario is known as the Big Rip. The name sounds dramatic, but the underlying physics is surprisingly elegant. The expansion of space would become so powerful that it would overcome every force holding matter together. First, galaxies. Then stars. Then planets. Then molecules. Then atoms. And finally, even the fabric of space-time itself. Everything would not explode. Everything would simply lose the ability to remain connected. Imagine a book whose pages slowly drift apart until every sentence is scattered across an infinite distance. The words still exist, but the story can never be read again. That image may be closer to the Big Rip than any explosion Hollywood has ever imagined. Fortunately, there is no evidence that this scenario is inevitable. Current observations remain consistent with dark energy behaving like a cosmological constant. But science has not ruled out other possibilities. And that uncertainty matters. Because it reminds us that the greatest questions in cosmology are still open. This is the part that almost no one notices. When people hear that scientists describe the universe with extraordinary precision, they often imagine that every major mystery has already been solved. The opposite is true. The better our measurements become, the more precisely we define the boundaries of our ignorance. Dark energy is perhaps the greatest example of this paradox. We can measure its effects with astonishing accuracy. We can predict how it influences the expansion of the universe. We can include it in equations that describe billions of light years of cosmic evolution. And yet we still cannot answer the simplest question of all. What is it? This is where philosophy quietly enters the conversation. Not because science has failed, but because science has carried us to the edge of what observation can currently reveal. Every civilization has lived beneath the same sky. For thousands of years, humanity searched for meaning by observing the stars. Today, our telescopes can peer billions of light years into the cosmos. Our satellites measure tiny fluctuations left over from the earliest moments after the Big Bang. Our detectors observe black holes colliding across unimaginable distances. And still, one invisible component dominates the evolution of everything we see. There is something profoundly humbling about that. It reminds us that knowledge is not a destination. It is a horizon. Every time we reach it, another horizon appears beyond. Perhaps that is the true lesson of dark energy. Not that the universe is trying to hide its secrets from us, but that reality is deeper than any single generation can fully comprehend. Perhaps the greatest discoveries still lie ahead, waiting for questions that humanity has not yet learned how to ask. Perhaps the terrifying truth about dark energy is not that it could silently destroy the universe. The truly unsettling possibility is that it is quietly revealing how little we still understand about reality itself. Perhaps the greatest mystery is not hidden somewhere beyond the stars. Perhaps it has surrounded us from the very beginning, woven into the fabric of empty space, patiently waiting for a civilization capable of asking the right question. And if that day ever comes, we may discover that the end of the universe was never the real mystery. The greatest mystery was why there was a universe at all.